Hello and welcome to this tutorial on the ideal operational amplifier, commonly known as the op-amp. An op-amp is a crucial component in analog electronics, widely used in various applications like signal processing, control systems, and instrumentation. Today, we'll delve into the ideal op-amp, its characteristics, and how it works. An ideal op-amp is a theoretical device that is used to simplify the analysis of electronic circuits. It is characterized by several perfect attributes that do not exist in real-world op-amps but help us understand how they should ideally perform. These characteristics include: first, infinite open-loop gain. The open-loop gain is the amplification provided by the op-amp without any feedback. In an ideal op-amp, this gain is infinite, meaning even a tiny difference between the input voltages can result in a very large output voltage. Second, infinite input resistance. This means that the op-amp draws no current from the input signal source. As a result, it does not load the source, ensuring that the input voltage remains unchanged. Third, zero output resistance. This allows the op-amp to deliver as much current as needed to the load without any loss in output voltage. It can drive any load perfectly. Fourth, infinite bandwidth. An ideal op-amp can amplify signals of any frequency without any attenuation. This means it has a flat frequency response over the entire spectrum. Fifth, zero offset voltage. When the input differential voltage is zero, meaning both inputs are at the same voltage, the output voltage of an ideal op-amp is exactly zero. Before we discuss the ideal op-amp, let's look at the equivalent circuit of a non-ideal op-amp to understand the practical limitations. Input terminals. V1 is the inverting input. V2 is the non-inverting input. Vd is the differential input voltage, which is V2 minus V1. Output terminal. Vo is the output voltage. Internal resistances. Re is the input resistance, which should be high to minimize loading effects. Rho is the output resistance, which should be low to maximize the signal delivered to the load. Open loop voltage gain, A. The open-loop voltage gain, A, is the amplification factor of the op-amp. In a non-ideal op-amp, this gain is finite but very large. The output voltage, Vo, is given by Vo equals A times Vd, which equals A times V2 minus V1. Now, let's discuss the ideal op-amp model and its characteristics in more detail. Open-loop gain, A. In an ideal op-amp, the open-loop gain is considered infinite. This means that even the smallest difference between V2 and V1 will be amplified to a very large output voltage. Input resistance. The input resistance of an ideal op-amp is infinite. This implies that no current flows into the input terminals. In practical terms, this means I1 equals 0 and I2 equals 0, where I1 and I2 are the currents into the inverting and non-inverting inputs, respectively. Output resistance. The output resistance of an ideal op-amp is 0. This allows the op-amp to supply any amount of current to the load without a drop in output voltage. Bandwidth of operation. An ideal op-amp has an infinite bandwidth. This means it can amplify signals of any frequency equally well, from DC to the highest AC frequencies. Offset voltage. The offset voltage in an ideal op-amp is 0. This means that if the differential input voltage, Vd, is 0, meaning V1 equals V2, the output voltage, Vo, is also 0. When analyzing circuits using ideal op-amps, there are a few important rules to remember. No input current. Since the input resistance is infinite, no current flows into the input terminals. I1 equals 0. I2 equals 0. Voltage equality at input terminals. Due to the infinite open-loop gain, the voltage difference between the input terminals is 0 for practical purposes. This means V1 equals V2. Therefore, Vd equals V2 minus V1 equals 0. Output current. The output current, I/O, of an ideal op-amp is the sum of all currents leaving the op-amp. I/O equals I1 plus I2 plus I underscore plus I underscore minus. For an ideal op-amp, since I1 equals 0 and I2 equals 0, the output current, I/O, is the sum of the other currents. In summary, an ideal op-amp is a highly theoretical device with perfect characteristics that help simplify the analysis and design of electronic circuits. While real op-amps have limitations, understanding the ideal model provides a valuable foundation for working with these versatile components. By keeping in mind the ideal characteristics and rules, you can effectively analyze and design circuits that approximate ideal behavior.